What we observe about gases can be explained by several gas laws. You already know that a gas can be impacted by the temperature that it's at, the pressure that is within it and outside it, the volume it occupies, and the amount of particles that we have, or the number of moles of gas that are present. One of the big things to remember is that gases are very different from solids and liquids. A solid and a liquid have a defined volume. A solid has a defined shape. A gas has neither of that. It expands to fill its container. Because of all the space between the particles, it is highly compressible. Because there are so few particles in such a huge volume, gases always have extremely low densities. Now, the reason for this is what's known as the kinetic molecular theory. The kinetic molecular theory is, in essence, a series of postulates that explain how a gas behaves under all conditions. First and foremost, gases are composed of particles, most typically molecules. These particles are in constant random motion. They collide with each other in the walls of the container. When they collide with the container, that's what we interpret as pressure. The collisions are perfectly elastic. That means when a particle collides with another particle or collides with the side of the container, the kinetic energy that it had is the kinetic energy it leaves with. So the total kinetic energy is always being exchanged and never goes less. Kind of like when you drop a basketball, each time it bounces lower and lower because the kinetic energy is less each time. That's not the case in the terms of a gas. That never happens within a gas. The volume of the particles is insignificant compared with the space between them, so the space is much more significant, the space between the particles. They have no intermolecular forces with each other, meaning a gas, when it collides, you have that exchange of kinetic energy, but they don't hit each other. It's kind of like if I throw, you guys remember throwing those Velcro balls with the gloves that catch it, and if you throw it too hard, it doesn't stick to the glove? That's what's going on here. When the particles start sticking, that's when they're experiencing intermolecular forces. And lastly, that the kinetic energy of the particles is literally a direct result of the temperature of those particles. All of this goes in to explain the next few laws we're going to talk about. First up is Boyle's law. One of the things that we know about Boyle's law is that pressure and volume are inversely related, meaning as my volume increases, my pressure decreases. Or conversely, when my volume decreases, my pressure had to have increased. And this change is proportional. So if I double the pressure, I halve my volume. If I halved my volume, I doubled my pressure, and so on. Now, Charles' law is instead the relationship between temperature and volume. So we know that if we have a certain amount of gas and we heat it, that the volume it's going to occupy is greater. This was what we observe with hot air balloons. Gay-Lussac's is the relationship between temperature and pressure. Like volume, if I increase the temperature, my pressure increases. Now this ties back into our kinetic molecular theory, because if the temperature increases, that means the particles are moving faster and they're colliding with each other and the sides of the container more, and pressure is literally the result of those collisions. Now, all of these three can be put together into what's known as the combined gas law. So we have a fixed volume of gas at a certain temperature and pressure, and we change those conditions, we completely change the volume. One of the coolest ways to see this is to crush a can. So you heat a little water in that Coke can. When it's steaming and you can see the steam literally coming out, you have a certain volume of gas in that container at a certain temperature and exerting a pressure. And the pressure being exerted inside the can is equal to the atmospheric pressure on the outside. Now, when you invert that into the ice-cold bath that you can see in the second image, you results in a quick drop of temperature, a condensation of the gas inside because the water vapor has cooled off enough that it condensed. Now you have very little pressure being exerted on the can, and suddenly the atmospheric pressure is greater and the can crushes. Now, this actually ties into a little bit of Dalton's law. Dalton's law is what we know as the law of partial pressures. In other words, if I have a certain amount of gas, it's going to exert a certain pressure. And if I take a mixture of gases, each pressure from each gas is summed together for the total pressure of those gases. We observe this all the time when we look at air or when we air up a tire. So ultimately, the amount of gas affects the pressure. This also is tied into Avogadro's law. Ultimately, for Avogadro to figure out his number, in essence, that's 6.02 times 10 to the 23rd, he figured out that equal volumes of gases at the same temperature and pressure had to contain the same number of particles. So this is where we get 1 mole is 22.4 liters. Now this is true at STP, standard temperature and pressure. So 0 degrees Celsius, or 273 Kelvin, and 1 atmosphere. So no matter what gas you have, if it's at STP, it's going to occupy 22.4 liters. Now, ultimately, all of these laws combine into what we call the ideal gas law. PVNRT, PV equals nRT. So you can see that P is pressure, V volume, N the number of moles, R is the gas constant, we'll be talking about that, and T is temperature. Now, the key point about an ideal gas law is it's an imaginary gas. Any gas at room temperature and atmospheric pressure will behave like an ideal gas. And that means that the particles are infinitely small, so they have absolutely no impact on each other or what they occupy. Again, that distance between the particles is more important than the particles themselves. They do not interact with each other, so no intermolecular forces. And they behave, and we can predict their behavior with these characteristics every single time. Notice how we see kinetic molecular theory being played out in the ideal gas law. Now, there's a point here. If the ideal gas law were true, no gas would ever condense or deposit, meaning no gas would change state. So we know that this isn't true, but under normal atmospheric room temperature conditions, it's always true for every gas. Now, the gas law constant, our R value there, is basically a proportionality. You can think of it as a proportionality that helps the equation work. Ultimately, we rearrange our equation. We get R equals PV over NT. We know how to solve for R because we know at 1 atmosphere of pressure, 1 mole of gas at 273 Kelvin will occupy 22.4 liters. So when we solve that, we actually get a value. It's 0.0821 liter atmosphere mole kelvins. Notice, though, that there's 4 different units or 4 different values of R. Typically, we don't usually change the 22.4 liters, we don't change the 1 mole, we don't change the 273 Kelvin, we just change our units of pressure. So remember that 1 atmosphere is 760 millimeters of mercury, which is 760 torr, which is 101.3 kilopascals. And that's how we get all of those values. Now, you can solve various gas law calculations, which you will have in homework.